Hi FOM 12 students. This week we are starting chapter 6, which is on polynomial functions. Today we are going to do 6.1, which is exploring the graphs of polynomial functions. I'm going to call mine answer key. Okay, and it goes like this. The goal of this lesson is to identify characteristics of the graphs of polynomial functions. We will look at constant functions, linear functions, quadratic functions, and cubic functions. In general, guys, a polynomial function is one that can be written in the form that looks like this. F of x is equal to a subscript n times x to the n plus a subscript n minus 1 times x to the n minus 1. I know this formula looks a little complicated, but we'll see in the examples it's not too bad. Plus, could have a whole bunch of middle terms, and then at the end here, a1x times x plus a0, where n is a whole number. All of the n's have to be whole numbers, and a0, a1, all the way up to a subscript n are real numbers. The coefficient of the highest power of x is called the leading coefficient. Okay, and so some examples would be like f of x equals 5. This is what we call a constant function, because it's just a number 5. And it has degree 0 because the highest power of x is x to the 0. There are no x's. And the degree is the highest power of x. Another example would be like f of x equals 2x plus 1. This is called a linear function because its graph is a straight line. It is of degree 1 because the highest power of x is x to the 1. Next one on the list is, say, something like this. 2x squared minus x plus 1. This is called a quadratic function. And it is of degree 2 because the highest power of x is x to the 2. So notice, guys, that a polynomial function really is a bunch of powers of x terms added or subtracted together. Excuse me. Another example is 4x cubed plus 3x squared minus 2x. This is called a cubic function. And it is of degree 3 because the highest power of x is x to the 3, as you can see. Okay, so yeah, so the powers of x, it has to be x to a whole number. And the numbers in front can be, you can have coefficients of any numbers in front of those powers of x. Graphically speaking, here's what we have. Constant functions are degree 0. One example would be this constant function. This is f of x equals 4. Okay, that's a constant function where the y value always remains at 4. And we could have something like this as well. This is f of x equals negative 2. Linear function, first degree functions, either slope up and to the right, or down and to the right. Okay, so we could have this. This one is f of x. F of x just takes the place of y, so we could write y, but we write it as f of x equals 2x plus 1. It's very similar to y equals mx plus b. That means that our slope is 2 and b, our y-intercept, is 1, as we can see from the graph. Another example would be something like this. This is f of x equals negative 1/3 x minus 1. The slope is negative 1/3, and b, the y-intercept, is negative 1. Quadratic functions are second-degree functions, and an example could be like this. The graphs of quadratic functions are these sort of U-shaped graphs called parabolas. And we could have one over here. They either face up or they face down like this. Okay, and finally, cubic functions, which are third-degree functions. These are what we call the John Travolta graphs, kind of like Saturday Night Fever. So one side end points up, the other end points down. And an example could be x cubed plus 3x squared minus 2x plus 5. Okay, or the graph can be going this way. F of x equals negative 2x cubed minus 6x squared minus 5x plus 6. Okay, and so that's very roughly what cubic functions look like. Okay, so let's do some examples. It says use technology to graph each polynomial function below, determine the x-intercepts, y-intercepts, domain range, end behavior, and number of turning points. Okay, so it's going to want us to find the x-intercepts, the y-intercepts, the domain and range, the end behavior, and the number of turning points. Okay, and so let's give this a try. I am going to get out my virtual Casio, and actually, as it turns out, guys, I should be able to send you a link for you to be able to download a calculator very similar to this onto a desktop computer. And so we will go menu and go down to graph and make sure all of your Y's are clear. Everything is cleared out. There's 20 graphs that we could do. So in Y1, I am going to type in this 2x minus 4 graph. 2x is this key that's got the theta and the capital T on it as well. So 2x minus 4. and you press the blue execute, and then notice in the upper right corner here it says draw. That's above the F6 key, so I press draw, and that's what the graph looks like. If you want to get a better window, you can go V window, F3, press F3 again, and that standardizes it to 10 by 10. If I go exit and draw, that's what my graph looks like. Okay, the x-intercepts we can actually get, I think it's under G-solve, so you go Shift F5, and it's got, oh, root is the x-intercept, so we'll just go root. So we have a root at 2, 0. There's the x-intercept. X-intercept at 2. Let's go G-solve. We can get the y-intercept. The y-ICPT is 0, negative 4. So y-intercept, negative 4. And then we can connect those dots because this is a linear function. Okay, so very roughly the graph looks like that. Okay, the domain is all possible x values used for this graph, and when the graph goes to the left and right forever, that means it's using all real numbers for the domain. And the graph goes up and down forever, covers the whole y-axis, so the range is all real as well. The end behavior has to do with the quadrants of the xy plane, and the quadrants go like this. This is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. You can kind of see how there's sort of 4 rectangles formed by the xy axes. And for end behavior, we could just say that the line extends. As we move left to right, the line extends from quadrant 3 to quadrant 1, and I'm going to abbreviate it as quad 1 now. And the number of turning points for a linear function, does this graph turn and go back at any point? No, so there are 0 turning points. All right, let's try another one. F of x equals x squared plus 2. Remember, they want us to find x-intercepts, y-intercepts, domain and range, end behavior, and number of turning points. Okay, so let's get out the calculator. Let's go exit. We'll go up to Y1 and see how it says del above F2. That's for delete. So I'm going to go F2. It says delete formula. Yes, F1, no, F6. So I'll press F1. There we go. And now I'm going to type in x squared. The squared is, see how there's an x squared beside the red alpha button? You have to press the x button first though, and then you go squared, and then plus 2. Press blue execute, and F6 for draw. Let's go G-solve. Root is the x-intercept. Oh, not found. There are no x-intercepts. That makes sense because the graph is not touching the x-axis. So none. Let's go G-solve. The y-intercept is y-ICPT. That's F4. The y-intercept is at 0, 2. Okay, so y-intercept at 2. And very roughly, the graph goes like this. Okay, so we're just doing rough sketches. The domain is all of the x values used, how far to the left and right the graph goes. So it goes that far left, and it keeps going this way to the right. So the domain is all real. And the range is how high and low on the y-axis it goes. So there's the lowest y point, and then the graph goes up from there. So we write that as y being less than infinity, but greater than or equal to, I was going to put -2, but it's actually +2, right, on the y-axis? Okay, so there's the range. So now this is up to infinity. Okay, so like we could even do this for the domain if you wanted to do that as well. The end behavior, the curve extends from quad 2 to quad 1. And number of turning points, the graph comes down, kind of turns back, and goes back up. So there is one turning point right at the tip of the parabola, right? All right, and letter C. Again, they want us to find x-intercepts, y-int, domain, range, end behavior, and number of turning points. Okay, so let's graph this. I'm going to go exit, go up there, go delete, yes. Now we have to do x to the power of 3 minus 2x squared minus 5x plus 6, execute and draw. Perfect. Let's do root. So there's the first x-intercept at -2. And then I think you can arrow to the right, yes, and it goes to the next root at 1. And arrow to the right, and the next root is at 3. And let's go F5 for gsolve again, F4 for the y-intercept, which is at 0, 6. Okay, so we can see that the graph roughly goes like this. Okay, so x-intercepts are at -2, 1, and 3. The y-intercept is up at 6. The domain. The graph goes this way forever, and it goes this way forever, so all real. In the range, the graph will go up forever and cover the whole y-axis that way, and down forever as well, so also all real. Okay, or you can do the cool calculus notation if you want. The end behavior. The curve extends from quad 3 to quad 1. And the number of turning points goes up to the top of the hill, turns back, goes down, and then gets to the bottom of this other little valley and turns up. So there are 2 turning points. All right, guys, so that is lesson 1 in chapter 6. The homework is from the textbook. I will send this to you as well, so you can read those pages and then try a few questions on page 383. Okay, so I will send you that material, and as mentioned, I'll also send you a link for the virtual graphing calculator that you can download, or you can even try Desmos if you want to do that instead, but I would probably encourage you to try to get this calculator because we're going to do something called line of best fit later on. Okay, there you go, everybody. I will talk to you soon.